on this question, we want to analyze the graph of the rational function r of x equals 5x plus 5 over 2x plus 4. And we're going to go through several steps in solving this problem. And the first step is to write this function as a single rational expression. And this is already like that. We have one fraction. And then we're going to factor the numerator and denominator. So our numerator has a common factor of 5. I can factor that 5 out to get 5 times x plus 1. And the denominator has a common factor of 2, so I can factor out the 2 to get x plus 2. So this rational function, written in factored form, I notice that it doesn't have any common factors. So it's already a reduced rational function. So next we're going to look at the domain of this rational function r of x. And with rational functions, we have one concern, and that is the denominator. The reason why the denominator is a concern is because dividing by 0 is undefined. So with rational expressions that have a variable in the denominator, you have that possibility of creating a 0 in the denominator. So to find the domain of the rational function, we're going to take the expression in the denominator, 2 times x plus 2, and we're going to set that equal to 0. I can get rid of that 2 by dividing by 2 on both sides. And I have x plus 2 equals 0. And subtract 2 on both sides, and that gives x equals -2. So this -2, we call this a restricted value, because that's going to cause the denominator to equal 0 and the expression to be undefined. We need to exclude this restricted value from the domain. Now there are two common ways of writing the domain, and that is in interval notation and also in set builder notation. So in interval notation, we would think of the real number line as -infinity to infinity, and then take that one value of -2 out of the set of real numbers. We're going to write that in two intervals, the interval to the left of -2 and the interval to the right. The interval to the left would be -infinity to -2. That's all the numbers that are less than -2. And the interval to the right would start with -2 and go to infinity. So this would be writing our domain in interval notation. Now with set builder notation, we write curly braces to indicate that we're talking about a set of numbers. And our domain are a set of x values. And those x values can be any real number except for -2. So we write this vertical bar. This vertical bar, we say it as such that, but behind the vertical bar are any conditions that we put on the numbers in the set. So we only have one rule, and that is that x cannot equal -2. Other than that, any other real number can be included in the set. So you can write the domain in interval notation as -infinity to -2, union with -2 to infinity, or you can write it in set builder notation as any real number not equal to -2. So the next thing that we're going to look at are the intercepts of the graph. We're going to look for X-intercepts and Y-intercepts. Usually Y-intercepts are a little bit easier to find, so we'll start with that. So to find a y-intercept, we're going to let x equal 0. I'll substitute a 0 into my function r of x. That will give 5 times 0 plus 5 over 2 times 0 plus 4. And that leaves me with 5 over 4. And so we have a y-intercept of 0, 5 over 4. Then I want to find the x-intercept. Find the x-intercept, I'm going to let y equal 0. And we don't have a y in the equation because we're using function notation. So we have to keep in mind that r of x is the same thing as y. So we're going to set r of x equals 0. That's going to give us the equation 0 equals 5x plus 5 over 2x plus 4. I'm going to solve this equation by multiplying both sides by the denominator. 2x plus 4 times 0 is 0. And on the right-hand side, multiplying by the denominator cancels out the denominator, leaving me with just 5x plus 5. And I can solve. I'm going to subtract 5 on both sides, giving me 5x equals negative 5. Divide both sides by 5, and I get 5 equals negative 1. So this function, this rational function, has an x-intercept at negative 1, 0. Now, when we studied polynomial functions, we learned about the behavior of x-intercepts. The graph can either cross or touch at the x-intercept. And we determine whether the graph crosses or touches by the multiplicity of that x-intercept, or that 0. So what we want to do is we want to determine the behavior of our x-intercept of negative 1. And we do that by taking a look at our rational function. So this rational function, remember, is r of x equal to 5x plus 5 over 2x plus 4. We wrote that in factored form as 5 times x plus 1 over 2 times x plus 2. And if we analyze this factor of x plus 1, this factor of x plus 1 is the factor that matches our x-intercept of negative 1. And this factor is only raised to the first power, so that means that that factor has a multiplicity of 1. And because that multiplicity is odd, we know that the graph will cross at that x-intercept. So we know that we have a factor of x plus 1, which has a 0 of negative 1. That 0 has a multiplicity of 1, and because it is an odd number, we know that our x-intercept will cross the x-axis. Our graph will cross the x-axis at that x-intercept. Okay, so now what we're going to do is we're going to look for vertical asymptotes. And when we look for vertical asymptotes, what we do is we keep in mind what we did earlier. So remember earlier we found the domain and we found a restricted value of x equals negative 2. That restricted value is either going to be a vertical asymptote or it's going to be a removable discontinuity. And in shorthand, we usually call these holes in the graph. So when we look at, and then I have this x plus 2 here, shouldn't be there. When we have our rational function in factored form, we can look to see that factor. This is the factor that produced the restricted value of -2. You're going to look to see if that has a common factor in the numerator. You're going to look to see if you have another factor of x plus 2. If you have another factor of x plus 2 in the numerator, you have a removable discontinuity. But if you don't, you have a vertical asymptote. So since our function doesn't have that common factor in the numerator, we know that there is a vertical asymptote at x equals -2. So now that we know that we have a vertical asymptote, we want to know what that looks like. What does that look like on the graph? So we want to determine the behavior of the graph on either side of that vertical asymptote. So when we're thinking about the behavior of a vertical asymptote, we want to keep in mind the definition of a vertical asymptote. With that definition, what we know is that as x approaches that asymptote, in our case, -2, we know that the y has two choices. Your y's will approach infinity, or your y will approach -infinity. So we really have four scenarios that could happen when we have a vertical asymptote. So you could have your vertical asymptote, let's say at -2, and on both sides they go to positive infinity. Or you could have your vertical asymptote at -2, and on both sides go to -infinity. Or you could have them going in opposite directions. So maybe the right goes to positive infinity and the left goes to -infinity. Or maybe the left goes to infinity and the right goes to -infinity. So these are the four choices, and we need to figure out which one is the behavior near our asymptote. So the way we do that is really just with a test value. So we have our rational function, 5x plus 5 over 2x plus 4. And we want to figure out the behavior around -2. I'm going to pick a test point on either side of -2, like -2.1 and -1.9, and that's going to tell me the behavior on either side. So let's test that. R of -2.1 would be 5 times -2.1 plus 5 over 2 times -2.1 plus 4. So I'm going to get my calculator. And I've got 5 times -2.1. It's going to be a -10.5 plus 5. And in the denominator, 2 times 2.1, -2.1, would be a -4.2 plus 4. And really the important part here is whether it comes out positive or negative. So we've got a negative in the numerator and a negative in the denominator, and negative divided by negative is positive. So now I know, because that came out positive, that on the left-hand side, I'm going to be approaching positive infinity. So then I'll check -1.9. So 5 times negative 1.9 plus 5 for 2 times negative 1.9 plus 4. That's 5 times negative 1.9. That will be a negative 9.5 plus 5. 2 times negative 1.9. That is a negative 3.8 plus 4. And this is going to be a negative over a positive, which gives me a negative. So I know on the other side, it's going to go to negative infinity. So on the right side, it goes to negative infinity. So we figured out that our behavior looks like this one right here. So for the next part, we're going to find the other type of asymptotes, horizontal or oblique asymptotes. And finding these horizontal or oblique asymptotes in an algebra class involves some memorizing of rules. The actual calculations involve an operation called limits, which is usually taught in a calculus class. So we're going to take this group of summarized rules that's been created for us to determine the asymptotes. So these rules involve the degree. So we need to know the degree of the numerator, which we usually call n. And the degree of this numerator, we have x to the first power, and so we have a degree of 1. This is the degree of the numerator. And then we need to know m, which is the degree of the denominator. And it also is 1, x to the first power. It's a degree of 1. We take the highest power if we have more than one variable there. And we compare them. And one of the comparisons involves them being equal to each other. I typically call this case 2, where n is equal to m. Anytime we have the degree of the numerator equal to the degree of the denominator, we are going to have a horizontal asymptote. And that horizontal asymptote is y equals the ratio of the leading coefficients. And the leading coefficients are these coefficients that are attached to the highest degree term. So the horizontal asymptote for this example is y equals 5 over 2. So we're going to have a horizontal asymptote at y equals 5 over 2. So the next part involves determining whether we have any points where the graph intersects the horizontal asymptote that we just found. So we want to find where the graph intersects or crosses the horizontal asymptote that we just found. So the graph we're referring to is the graph of 5x plus 5 over 2x plus 4. And the horizontal asymptote that we found is 5 over 2. And if they cross each other or intersect each other, that means they have to be equal to each other. So we can create this equation where you set the function equal to the asymptote that you just found, and that's going to tell you any points where they cross each other or where they equal each other. So I'll solve this equation. I'll do that with cross multiplication. So if we multiply 2 times 5x plus 5 equals 5 times 2x plus 4, we would get 10x plus 10 equals 10x plus 8. And as you solve this equation, the variables end up canceling each other out, and we get 10 equals 8. This is obviously false, and so that tells me that this is an equation with no solution. So for this particular example, the graph will not cross the horizontal asymptote. It does not cross or intersect the horizontal asymptote. So we're going to put all of this together in order to sketch the graph of our rational function. So I wrote down everything that we figured out. We have a vertical asymptote at x equals -2, a horizontal asymptote at y equals 5/2. We found both an x-intercept and y-intercept, and if you'll recall, we did find that our graph crosses at that x-intercept. We have a y-intercept at 0.5. We know the graph does not cross the horizontal asymptote. So we're going to take all that information and draw a sketch of this graph. So I'll start by putting in the asymptotes and the individual points that we found. So I'm going to make this really big. So let's make this -1 and -2. We have a vertical asymptote. I'll label it vertical asymptote at x equals -2. Then we have a horizontal asymptote at y equals 5/2. That's 2.5. The horizontal asymptote at y equals 2.5, or y equals 5/2. We have -1, 0 as an x-intercept, and 0 and 5/4. 5/4, that's going to be 1.25. So that'll be about right here. We also found that the graph will go to positive infinity on the left and negative infinity on the right. So we know that these 2 points will connect to each other, and on the right of that vertical asymptote, it will go to negative infinity. If we continue to follow this line, it should approach the horizontal asymptote by definition. And then we also know that the other side of the graph will be, or the other side of the asymptote will go to positive infinity. So this gives us a sketch of our rational function. Thank you for checking out my videos. Have a great day.